Welcome, everyone. Thank you for joining our conversation on the COVID-19 Enterprise Data Lake. My name is Arjuna Chala, and I'll be co-presenting the track with our technology experts, Lili and Roger Dab. Let me start by asking you a few questions. In the context of COVID-19, do you feel safe when you go to a grocery store? Do you feel safe to go for a walk? Do you feel safe to go to a restaurant? Now, let me ask the same question in a different manner. Would you feel safer to go to a grocery store if you know the risk of getting COVID-19 is very low, or medium, or high? This, in a sense, brings us to the goal of our COVID-19 project: to remove the confusion created by the information overload and provide a concrete plan of action. We really want to focus on two aspects. What is the current situation? And what will be the situation in 2 to 3 weeks from now? Now, this project is a collaboration between multiple parties. The wonderful folks at Florida Atlantic University, Dr. Barco, Professor Benaz, and PhD student Murtada, Oxford University represented by Dr. Ning, and PhD student Yutang. Several collaborators from both LexisNexis and outside are also involved. This is a National Science Foundation funded project. Last but not least, we have some wonderful external contributors like Ellie Carl, who worked through this even while facing a wildfire situation in Washington State. Let us talk about some of the data sources we use in the project. While we started with the data from Johns Hopkins, we have grown the data to include COVID testing from the COVID tracking project, population data from the United Nations and US government, daily cell phone density data from both Google and Apple. We are now working on acquiring data around tourism and transportation infrastructure, socioeconomic data, flight schedules, and other sources of people density and movement data. I do not want to cover too many details on this slide, as other speakers have touched upon them already, or are covering them in the near future. But I do want to mention a few new features that has helped our project. The new elastic features of HPCC has helped scale HPCC on demand. A comprehensive data dictionary about the data lake assets has helped all the collaborators collaborate in a very efficient manner. And the new built-in BI and machine learning tools has made visualizing and predictions a breeze. The overall component architecture is actually very straightforward. Most of the complexity around ingesting the data, cleaning, and analyzing the data is solved by HPCC. A React single-page application directly connects to Roxy services. And Real BI provides for ad hoc type of reporting. Last but not least, Tombolo provides for tracking and documenting the assets of the data lake. Now, Roger and Lili are going to show you the cool stuff. If you have any questions, please send it to us via the chat window. We will address the questions at the very end. Roger, please take it from here.
Just 1 second. I'm sharing my screen. All right, so this is our COVID-19 tracker system. And I'm going to start by giving you a quick overview of the user interface. Then I'll focus on the metrics that we've developed and the process that we've used to develop them. So right now, you're looking at the infection state across the countries in the world. Infection state is a qualitative metric that we developed that indicates the state of the infection within each country. As usual, green is good and red is bad. Green represents locations that are recovering or recovered. Red represents locations that are emerging or spreading. And yellow is a neutral color. That's for a location that's stabilized. And orange represents locations that are near stabilized.
Hey, Roger, I'm
Yes.
not sure, but I don't see your screen share. I'm not sure if others can see it either.
Okay, let me revisit that. Okay. Can you see that now?
It's still showing the last slide that I presented.
Okay. Apologies.
There, much better.
Okay.
Yeah, so now you're allowed to start from the beginning there.
Yes.
Thank you.
So I'm going to give you a quick tour of the user interface, and then we'll talk about the metrics. So right now we're looking at the infection state across countries in the world. And green represents recovered or recovering locations. Red represents emerging or spreading locations. Yellow means stabilized, and the orange is almost stabilized. So I can hover over any location, and I can see metrics associated with that location. I can also change my perspective here. So right now we're looking at infection state. I can switch to contagion risk. And this uses the same color scheme to indicate countries that have the highest contagion risk. So if I go to Spain here, I'll see that there's a 60% risk, France 52%, Argentina 74%, and the United States 49%. And I'll be explaining exactly what that means. We can also look at other attributes such as number of new cases. You can see that India has now become the biggest source of new cases. New deaths. You can see it spread. India is again the highest, but Brazil and the US are up there as well. We look at the cases, per capita cases. You see that the United States is the highest, and Brazil, and several other countries, South Africa, Saudi Arabia, France, Spain, and Sweden, all have very high per capita case rates. Death rates, you get a different perspective, and then you can look at total cases and total deaths. So Arjuna has created this visualization that lets you look at the infection from many different perspectives. So right now I'm looking at the world level. And for any level that you're looking at, there's a vast amount of data that you can look at. So you can go to the commentary. These tabs up here allow you to navigate through the various views. So here's a commentary about the world. We've already seen the map. I can go to a list view, and this shows me all of the components of that location. So in this case, we're looking at the world. So the components are the various countries that make up the world. Now I can sort this by any characteristics. So if I want to see who's in the worst infection state, I see the spreading countries at the top. I want to see who's the worst contagion risk. We have Israel with a 96% contagion risk. And I can also use any of the other characteristics there. So the next tab is stats. And this is where we have all of our analyses presented in kind of a raw form. And we'll spend a lot of time here, so I'm not going to spend time right now. The next zone is trends, and this lets you look at things like the infection growth rate over time, the number of cases and deaths over time. And finally, a hotspots list that let us see in prioritized order the locations that have the most, that are having the most difficulty and that are most in need of attention. And of course, you can drill into these to go directly to that country. And there's a write-up commentary on each of those hotspots as well. So we wanted to create a system that would be useful for researchers, such as our university partners, for health officials, and as well as for curious individuals. So I'll take you through the analytic features, but as I do, I want to provide insight into the process by which they're developed. So I'm going to take you to our GitHub site very briefly. This button up at the top takes you right there. And this contains all of our documentation about the tracker. We've described every attribute, every algorithm that we use. And very importantly here is a causal model. We developed this early in the project and refined it ever since. And we constantly return to this as a way of judging our metrics, way of developing our metrics and evaluating whether they actually measure what we're attempting to measure. So now I'm going to take you back to the user interface, and we'll take a look at some of our metrics. I'm going to go to the United States. Oh, one thing I forgot to show you is that you can drill down into any location that provides data. So I can drill down into Spain. And see the various regions of Spain and look at any of the perspectives for that region. I can drill into the United States and see the various states. I can drill down into a state and provide a view at the county level. And all the same data that you have at the country level, you have all the way down to the county level. All right, so I'm going back to the United States, and we'll take a look at the metrics. So one of the most important epidemiological metrics is known as R. And R stands for the reproductive growth rate. And it's the effective growth rate of the infection. Specifically, it's the number of people an infected individual is expected to infect during the course of their illness. So if R is 1, then the average individual will infect one other person. You can see here for the United States currently, R is 0.94, so it's a little bit less than 1. 1 is a steady state for the infection. If R is greater than 1, then the infection will grow exponentially. And if R is less than 1, the infection will shrink exponentially. R is the exponential base for that growth. Unfortunately, we can't observe R. It's theoretical. The available data provides a number of cumulative cases, deaths, and sometimes hospitalizations. So we can estimate R by growth in cases. And the CR is the growth in cases, as well as by the growth in deaths, which we call MR. Each of the measures have their own pros and cons. Deaths lags cases, so cases are closer to real time. On the other hand, cases are impacted by testing availability and test policy. Deaths, much less so. These relationships can be seen in our causal model. So we combine the two measures to estimate the overall R. In this case, you see the case rate is 0.97, mortality rate is 0.92, and we develop an estimate of R at 0.94. So we noticed that the widely used Johns Hopkins data has a lot of problems when we try to use it for differential analysis, such as growth rates. Perfectly adequate for what it was intended to is to show the cumulative numbers. But when you go to perform analysis, ineffective. So it'd be reasonable to think that we could take the cumulative number of cases from one day, subtract the previous day, and get the difference to find the number of new cases, for example. Turns out that that's not the case. Various health authorities commonly make adjustments to the case and death numbers, presumably due to changes in policy, correction of errors, late data reporting, etc. These adjustments are made not to the days where the data originated, but are usually dumped into the most recent day. As a result, cumulative numbers are often less on a given day than they were the previous day. Sometimes impossibly many new cases are implied by huge growth from one day to the next. Locations are sometimes combined into a single location, or a single location is split into multiples. This creates discontinuous time series. These out-of-time sequence adjustments are known as anachronous data and make meaningful analysis difficult. We found that we needed to design a filter that would remove most of these effects without delaying the signal in the data. This is very critical for organizations like Florida Atlantic University, who are trying to make predictions about the evolution of the pandemic. Researchers using other data sources will need to discover the same issues and develop their own approach to removing the noise. From a data enrichment point of view, we discovered several different ways that even widely used data from reliable sources can misbehave very badly when being used for deeper analysis than that for which they were designed. We were surprised to see how rapidly the effective growth rate changes in locations all around the world. We noticed that even in developing countries with little health infrastructure, that high R values indicating exponential growth typically subside within a few weeks. We believe that's because people naturally respond to the news or to their neighbors' stories, and very quickly decide to socially distance, even without government intervention, when the growth rate becomes very high. So we were able to consult our causal model and demonstrate that the primary driver of changes in growth rate is changes in social behavior. This allowed us to develop the social distance indicator, which, like all of our indicators, use positive values to indicate positive outcomes and negative values for negative outcomes. You can see that at 0.16, our social distance indicator for the United States shows that the social distance is increasing. When doing data enrichment, we were surprised by the rapid change in R. Surprises often signal that there is an opportunity to create insight. We wanted a qualitative metric that let us understand the phase of the infection at a given location, so we developed the infection state, which you see over here. In this case, the United States is stabilized. As I showed earlier, any location can be in one of several states: spreading, emerging, stabilizing, stabilized, recovering, or recovered. We studied the ratio of the case rate and the mortality rate and found that there are three causes of change in this ratio: changes in testing availability, changes in medical care, and transitions from growth to recovery or recovery to growth. By ignoring the transition periods, we were able to develop a medical quality indicator metric that signals a negative value when either testing availability or medical care becomes overloaded. We produced some other standard epidemiological metrics: case fatality rate, infection fatality rate, and immune percentage. While case fatality rate is rather straightforward calculation, infection fatality and immune percent requires an estimation of infections versus cases, which we have little visibility into. So we calculate a very rough approximation using a fudge factor, which we call the infection to case ratio. We calibrate this ratio using various antibody studies and CDC estimates to be able to approximate the number of actual infections, including asymptomatic, subclinical, and clinical. While we know this approach is not optimal, the real factor would need to vary by both location and time. It may be better than no estimate at all, an important lesson for data enrichment. We've defined a much better method to use in future release, but have not had a chance to implement it yet. We developed a pair of forward-looking metrics: the short-term indicator and the early warning indicator. Short-term indicator attempts to forecast movements in R over a period of a few days, and the early warning indicator detects transition points when growth is expected to rapidly increase or decrease. Florida Atlantic University is working on a predictor of future growth using neural networks and LSTM, which we expect to yield some useful longer-term predictors. This requires real-time inputs regarding movement of individuals using cell phone mobility data, among other things. Remember, we mentioned that the biggest factor for the growth rate is the social behavior, and this allows us to observe social behavior, which should predict changes in the infection rate. We were looking for a metric that would help individuals assess their risk in venturing into a given location, and develop the contagion risk metric. This is defined as the likelihood of meeting at least one infected individual during 100 random encounters, such as you might have if you stroll down a city street, go to a mall, go to a movie theater, or a restaurant, or an airport. The fact that this is always between 0 and 100, in this case 49.1%, makes it easily digestible versus something like active cases per 100,000 population, which we see over on the left side here. So 2,266 per 100,000 doesn't mean much to me, but 49% is much more digestible. From a data enrichment point of view, an easily digest metric has more value than one that may convey the same information, but is harder to understand and interpret. We wanted to be able to identify problematic locations to help health officials in knowing where to apply their resources. So we created a heat index, combining various metrics to indicate the seriousness of the situation in any location. This is calibrated such that values greater than 1 indicate that intervention is likely needed. This drives our hotspots view, which displays the locations needing attention in prioritized order. In this case, you can see Wisconsin, New Hampshire, Wyoming, New York, and Utah as being sites that are in need of intervention. So going back to the US, we recognize that the metrics, while very useful, required quite a bit of understanding in order to interpret. So we developed an automated, context-sensitive commentary that utilizes all of the metrics plus some expert interpretation to provide a plain English view into the state of the infection at each location, country, state, or county. Let's take a look at a couple of these. I'm going to go to Wisconsin. As of October 4th, 2020, Wisconsin has worsened to a spreading state from a previous state of stabilizing. The infection is quickly increasing. R is 1.65. At this growth rate, new infections and deaths will double every 14 days. This outbreak is beyond containment with 24,000 active cases and requires mitigation. Here's another variable that we haven't talked about, another metric. This is the 4th surge in infections, which started on the week of August 31st, 2020. We track each surge and we can analyze the infection growth by surges. With 16,000 new cases and 76 new deaths, this is the worst week yet for cases and deaths during this surge. The contagion risk is extremely high at 87.9%. This is the likelihood of meeting an infected person during 100 random encounters. It appears that the level of social distance has increased slightly, resulting in lower levels of infection growth. The mortality rate is growing faster than the case rate, implying that there may be a deterioration in medical conditions, probably indicating an overload of the local medical capacity. With only 76 deaths, this could easily be caused by a statistical or reporting anomaly. U.S. Wisconsin is currently in the hotspot list due to a rapid increase in cases. The case fatality rate is estimated at 1.2%. This is lower than the average of 3.1%. Preliminary estimates suggest that 9% of the population may have been infected and presumed immune. This is not enough to significantly slow the spread of the virus. The preliminary estimation also implies an infection fatality rate of roughly 0.2%. The short-term indicator suggests that the infection is likely to slow somewhat over the next few days. So you can see there's a lot of information in there and a lot of interpretation of the metrics, which can be very useful. Let me just take a look at one other state. I'm going to go to Florida, which is in a different state, and we get a different type of commentary depending on the state it's in. Florida remains in a stabilized state. Infection is slowly decreasing, 0.91. There are currently 24,000 active cases. At this rate, expect to see 16,000 new cases and 646 deaths per week. It's the 3rd surge of infections. The contagion risk is very high at 42.9%. Case fatality rate, 2.1. 16% of the population may have been infected. And the short-term indicators suggest the infection is likely to slow somewhat over the next few days. So that's our commentary. We think that's very useful for people at all levels to help understand the meaning of the metrics. And that commentary could not have been produced without first producing the metrics that drive it. Recently, Arjuna added a historical perspective to the user interface. I'll show you that. While we're just starting to utilize it, it became immediately obvious how much light it can shed on the evolution of the pandemic. It allows you to step forward or back in time. Oops. I'm going to do it for contagion risk. I'm going to step back all the way, and it also allows you to animate the progression. Here you see from the earliest data that we have on the virus, how it progresses in the United States week by week. We're now in July. Getting pretty bad. September, still pretty bad. So this is where we are today. So I have no doubt that this will lead us to additional insights and produce more added value. This is the way value develops in a data lake. Each advancement leads to new questions, which lead to new discoveries and a snowballing of value. At this point, I'd like to introduce my colleague, Lili, who developed the automation and curation aspects of the data lake.
Thank you, Roger. That's awesome demo. Can you see my screen right now?
Not yet, Lili. I think it's coming up. We're still seeing
Okay.
old screens.
Yep. No issues. Let's wait.
Yeah, now we can see it.
Okay, perfect. So thank you, Roger. That's awesome demo. And while you are watching this fancy front end, you may have a question is, how about the back end? Where's the back end? And one possible answer is like this in your mind. It's a traditional Excel wash view. In this view, we hardly can see how I locate or search my files. And that's the problem we firstly encountered. And as Roger introduced in the keynote session, when the data increasing on daily basis and fastly our data lake become a data swamp, it's hardly find information we need. And the second, in this view, we can find out that it's obviously no information about the context, how the data was created, and what is context, and even definitely no information about the compliance. So without this information, we moved on forward to our next solution, which is Tombolo. So Tombolo gives us a high-level view of our whole bigger picture of the pipeline. It gives us an end-to-end asset view. It provides a tracking lineage for the data. It also gives us a unified view for compliance, developers, product teams, and data scientists. So as a data curation system for HPCC systems, we use Tombolo as a backend core for the whole process. Now let me give you a detailed introduction for Tombolo in the following demo. Let me share my screen. Can you see my screen?
Yes, you can see it now.
Perfect. So let's first go through our workflow. In Tombolo, as we can see in the last slides, Tombolo really shows our whole pipeline as a whole. This is centralized location for all the assets. We can see the file, the jobs in the orange color, and the files in the blue color. No matter what kind of assets, it's all centralized in this one location. It automates our data pipeline solution consisting all the repeated jobs and encapsulate all those jobs and the files as workflows, as we can see here. It is the central location for all the assets. And then by simply connecting all the assets, we get the data lineage. We can see how the files evolving from the raw file to all the way down to a consumable file, such as matrix files by the front end. And now let's go to the details for each block in the workflow. We're starting from the left is a scheduler. We're periodically running the scheduler, kicking off the whole workflow. And the workflow gonna automatically kicking off all the jobs from spray, cleaning to analytics jobs, the weekly metrics. So every day we have data externally automatically update to the HPCC systems. And then the fourth job, spray, gonna automatically spraying the source file to raw file. And the raw file gonna go into the cleaning job. The semi-cleaned jobs, the files, the population files, the Johns Hopkins level files gonna fit into the ingest Johns Hopkins data jobs. And after this job, all the files gonna be consolidated as the 3-level cleaner files. Level 1 means country level, level 2 means state level, and level 3 means county level. And all this cleaner file gonna fit into the next job is the daily states, which aggregates all the files into the next level, statistics level files. We have 4 levels here. Level 0 is the world level, level 1 is the country level, and etc. And the last, we have analytics jobs, which is weekly metrics, producing all the metrics that are consumable by the front end. So this is the whole workflow for our COVID tracker projects. But then you may be wondering, how you make sure that the workflow running smooth without problem? You may wonder, maybe we wake up at midnight and look at the screen to make sure they are running, but that's not the case. So luckily, we are using Tombolo's instance view to tracking and monitoring our workflows. As you can see here, all the past instances or currently running instance are listed here. You can see that the status here is completed, and some instance may be failed, such as this one is with errors. Then Tombolo gonna instantly send out information such as cluster and the job information in the email to all the team members. Then we can also come back to the Tombolo, see the details in the instance, the detail view. In here, we have the red block shows it's filled, and when you click on it, it's gonna show the error messages. So here we can also click on the work unit ID to show the detail in your cluster. So using these functions really help all the team to keep eye on the projects, how the workflow being implemented and running in the back end without worrying at midnight all time to watching your screens to make sure it's running smooth. For the workflow that are completed without issue, like the last one we are running this morning, it's like this. It's going to be all marked in green check marks. So now we are sure that our flows are running smoothly without problem. Then that's not the end of story. For example, maybe data scientist is gonna ask, so in your data, how can I find the context? What is the information about which data should I use for my module? In this case, in Tomolo, we are using the job details or file details view to show the details, for example, the description of the file. For this file, matrix level 1 is about country level matrix. So in this case, data scientist is gonna say, okay, this country level matrix is perfect for my module purpose. Then I can go in detail to the layout view to see, okay, what's the matrix in the data? So layout view shows you all the details of each column level information, such as we have one attribute or field is called R, as Roger introduced. It's estimate of the effective reproductive rate. We also have SD indicator, which is the social distancing indicator, provides insight into the level of social distancing being practiced by a population. So with all this context of the data, it's really important for data engineers and data scientists to implementing their own module with all this field level details. Then how about compliance? Compliance come into this job file details field, go to the permissible purpose tab. This has the perfect information for all we need, which shows all the license we comply with. For this file, we have the US government works license. So in this case, we don't have to really go through all the complex meetings and emailing around saying which compliance we have been applied. And the next function is scrubs. So in our backend, we really needed this because for data engineers, we have so many instances. For example, I had one instance that in the morning, I suddenly realized our data don't have any country name information. I was like, what's going on? So I tracing down the details of every single file and it take a lot of time, but then realized the problem simply just because the country name format has been changed in the new data. So in this case, I'm really hoping I can use the scrub function in the coming release of Tomolo to enforcing my rule validation. For example, here I'm using non-empty rule to control the commentary area be non-empty. If anything violate this rule, then I can choose to either warning, shows a warning, or drop the records, or even fix it. So this function is really essential for us to make sure data quality and data consistency. And the next is the file preview that we can use to preview, have a glance of the data. It shows every single file, single field in this file. And the important part of this is we can only view the file if we are authorized the user of these projects, which is really a security aspect we love to use in Tomolo. And then last, data flow shows us all the data flows connected to this special file. Now the data scientist knows the context of the data. And the next question is, how can we really fast locate all the data I want? Then we can use the backend in Tomolo data dictionary view. Click on here, we can see all the data in my projects with all the descriptions. And also click on each single file, such as the file we showed before, matrix level 1. We can see the details of the file is the same, the descriptions and the layouts. And then the next question is, what about the other assets? In Tomolo also acting as a data catalog tool for our projects. We can see on the left navigation panel, we have assets section categorizing our assets into 4 types, like files, index, queries, and jobs and functions. If I want to find a job in my workflow, such as the ingesting Johns Hopkins data, I click on it. It will show me the job details view. In this view, one feature is very interesting is the Git Report function or feature. Right now, it's a hard-coded GitHub path, but in the coming release, we would love to using the feature like that to automatically pull in the latest commits from the Git account. And it really happened to me just lately that even last night, I received a call saying that, hey, Lili, I have new commits. Can you just put into your workflow? Sure, but what if we have this function? Tableau gonna automatically drag in the updates from the GitHub and automatically run the latest commits in your next workflow instance, which means we don't have to go through all this complex phone call and running the latest commits by manually coding in your workflow. So this function gonna really improve our team collaboration efficiency. Other features like the contacts and authors can really be helpful for compliance purpose. They can find the people who work on this file or job and ask for questions for different purposes. And we also have the input files, output files, the basic functions we have, also the data flows, shows all the data flow that this job belongs to. So this is a basic introduction of the core of our backend from Tableau view. And now let me go back to my slides and introduce the whole architecture of our backend. Some backup slides. So this is the whole architecture for our backend data curation, automation, and the tracking. As you can see here, still Tableau is a core in our backend, but still HPCC is the data lake solution for us to ingesting all the data from outside world, unstructured, structured, from database, from web page, from IoT devices, from local files. And Tableau using Kafka as a middle messenger to reading message from HPCC clusters. And then Tableau gonna using all those information playing a orchestrator role to using state machine, collaborating all these jobs and assets, making them into a whole workflow that flexibly controlled by Tableau. And these jobs can be from external Excel jobs, Roxy jobs, or even external. For example, we have some coming feature like taking the jobs from GitHub. If you have security concern for your code, you may set up a security alert in your GitHub. And then Tableau gonna automatically show you the alert or the security vulnerabilities when you're running the job in Tableau. And also we're gonna able to using, we're already able to using the non-HPCC components such as the Azure functions. And also Tableau gonna have, we also have API functionality for different applications externally using the API, maybe showing the workflow or using the schemas in Tableau from maybe Cloud IDE, Real BI. They can also using the API to show the features in Tableau. So this is our backend architecture. Last but not the least, we really appreciate all the helps and the contribution from our contributors. And we would love to call out their names: Dr. Barco, Dan Kemper, Roger, Dr. Bernays, Jesse, Ellie, Martadas, Arjuna, Chris, Bahar, Tim, and Jeremy. And on the right, please feel free go over our open source tools, our HPCC Enterprise Data Lake, the COVID-19 tracker, the Tombolo tool, ECL, Cloud IDE, and the Real BI. And feel free to contact us. We're always here. And we also have the coming, I think it's running whole day and a whole week, the Expo booth for all the open source tools, Tombolo, Cloud IDE, Real BI, even machine learning for HPCC systems. And that's it. Let me go back to Arjuna and Trish.
Thank you, Lili, and thank you, Roger. Great demos, both of you. So we do have a few questions. So let me go ahead and start asking those questions. Lili, if you can turn your camera on too, that would be great.
Yeah, sure.
So the first question, I think, Roger, it's for you. We have just seen in the UK an incident where allegedly an Excel spreadsheet used by health authorities failed to update, and consequently the number of cases were underreported, and tracing did not identify hundreds of potentially infected people. Do you have any thoughts about society's increased over-resilience on data and the problems that occur when bad data underpins our models? You're on mute, Roger. You're on mute. Can you unmute? Yeah.
Good. Excuse me. Yes, that is a problem, and I do not have a solution for that. But you know, one of the things that helps is having multiple sources for the data. Sources like ours, where we do some fairly deep analytics, helped identify those problems. We spotted that problem very quickly when it occurred in the UK. We didn't know the cause, of course, until it came out in the news. But we were able to detect the problem, and our filter was able to ameliorate a lot of the effect of it, because it saw that the changes were not organic, that they those wouldn't occur in the actual development of the infection. So we were able to filter them out and still present a reasonably accurate view of what was going on.
Yeah, and I think we ran into several data issues on a periodic basis, right? In the sense that sometimes the numbers, like for example, the death numbers were not accurate, in the sense, you know, if you look at in the United States, on certain days in the week, they used to report it accurately. On other days, they did not report it accurately. What was the solution around this? Can you describe that?
Yeah, so the solution was to add a smoothing filter that would basically average of the days without putting much delay into the information that we're receiving. And yeah, it's amazing how many ways data can misbehave. Lili and I were discussing that the other day, that that data can find very, very subtle ways to be wrong. Let's put it that way.
Absolutely. One other question, actually we have a few more, but has any action or specific benefit been taken based on these statistics and interpretations? So basically, Becky Champion is asking about, you know, based on the work that we have done, has there been any interpretations or statistics that has been useful for other people?
Well, we don't really know about much about our users. Right? A lot of people are using the system, but we don't know what they're doing with the data for the most part. But with our university partners, at Florida Atlantic University in particular, by using the data that's been previously cleaned and filtered, they can make much better predictions than they could if they were using any of the other data sources. Because of the problems that we've discovered and been able to fix, you get a much more consistent and reliable view of the data.
So in addition to that, Roger, I think we also have a few white papers that are being published by both, I think, Oxford University as well as FAU, based on the work that we have done here on the website.
Yes, there are quite a few papers being worked on, as well as a book being developed about the project.
Awesome. So another question, great present. Can we set up Tom so that for others who want more information regarding Tombolo or any of the tools that we just described, feel free to come to our expo booth, which is right after this conversation. There are other expo booths, obviously, at the same time, but there's a booth called specifically tools, and that is where we talk about Tombolo, Real BI, Cloud ID, and data profiling, data patterns, and all other tools. So feel free to come by and we can talk through the plans for the tools. But specifically to answer your question, Tombolo is ready to be used for any project. You can use it like a multi-tenancy type of implementation, or you can choose to implement it only for a specific project. It is up to you. Two models that can be really developed, in the sense you can have a hosting environment for Tombolo, or you can download it and use it in your own environment in a more private setup. So both models are supported. It's open source, completely available. You can go to the GitHub repository, download it, or you can try it using the URL that we have shown there. Okay. Roger, I think this is another question probably for you. What are the future plans for the COVID-19 project?
Oh, very good. So we're going to bring in the prediction that Florida Atlantic University is working on. We're just beginning to bring in more breadth of other data sources, the mobility data, etc., the travel data, and that opens up whole new avenues for insight. So we'll be working on that. And in particular, I mentioned that it's very difficult to assess the infection fatality rate and the number of people that, the percentage of people that are infected, because we don't know the actual number of infections out there. But we have a mechanism for doing that, which brings in the hospitalization data, and we can use that as a control to detect to get a better assessment of the number of actual infections out there. Perfect.
So one more thing I want to mention with regard to what we are thinking of as a new project or a sub-project for this is when somebody does take a flight, for example, let's say they take a flight from Atlanta to, let's say, Madrid. Right now, as you know, the infection rate and the contagion risk in Spain is pretty high, especially in the Madrid area. Then we should be able to provide a risk score for that flight, in the sense, what if you do take the flight, at the end of the flight, what is the possibility that you will actually get COVID-19? So that is something also that we're looking at, and we're looking at flight schedules data and also other data sources that can bring this information together and provide a solution around this. Some very interesting work that is going on. So we will keep you updated. And as you know, the site is constantly updated as well. So we come to the top of the hour now. Thank you all. Thank you for doing a great presentation, as well as doing the live demos. It was fantastic. Everybody, don't forget, just after this session, the booths are open. make sure you visit all the booths, look at all the posters that some of our university partners and students have developed, and then come to our booth with regard to looking at Tombolo and the other tools as well. Thank you again. Have a great day.
Thanks, everyone.
Thank you.